focus here is on linear equations. So these are equations with one variable for now that can basically fall into three categories. We can have what's called an identity, which is where the two sides of the equation end up just equaling each other. So we can see in the example here we have 6x minus 8 on the left. If we distribute, we're going to get 6x minus 4, which is going to clean up into 6x minus 8 on the right-hand side. And so what we can see is that it doesn't matter what we plug in for x, the two sides are going to be equal to each other. So an identity equation is one that's true for every real number. It doesn't matter if I plug in positive, negative, zero, fractions, decimals, rational, irrational, it's going to be true for everything. So that's the first circumstance. I'll jump to the third one here, which is also not our most common circumstance, is what's called a contradiction. And so this is when we have a equation that works for no value. So for example, 5x minus 7 equals 5x plus 7. It does not matter what I plug in for x. Again, 0, negative, positive, anything else, any number I can think of, nothing is going to work. So the equation is broken. So this is an equation that's false for every real number. So these are our rarest circumstances. Usually we have equations that fall into this middle category of being called a conditional, meaning the equation works for a particular value, or if we're talking about equations, not linear equations, but quadratics or polynomial equations, there may be multiple numbers, but it's a limited set of numbers, maybe a handful of numbers that'll work. So that's called a conditional. So that's what we see most often, are conditional equations. But these other circumstances pop up, so we should be aware of the terminology here. Identity, everything works. Contradiction, nothing works. Conditional, a number or two or three work. Now, most linear equations are not too challenging to solve. They might require a little distributive property, gathering like terms. We might have to move variables from one side of the equation to the other. As long as we're cautious with our algebra, we're going to be fine. But I did want to focus on one format of equation that can be a little bit tricky, which are rational equations. So if you'll remember, rational expressions are fractions involving variables. So rational equation is just going to have an equal sign in there. So we have an equation we have to solve. And so generally speaking, we want to try to obliterate those fractions as fast as we can. Fractions are a real pain to have to deal with. So in order to do that, what we can do is we can find what the common denominator is of all of the fractions that we see in the problem, and then multiply it by that common denominator over 1. So what that'll do is that'll eliminate all of our denominators and give us a little bit more straightforward equation to work with. So in this first one here, and I do need to remember to put that 6 over 1. We don't want to overlook that as well. So I see 3, 4, and 1 as my denominators. So my common denominator of all that is going to be 12. And so now I'm just going to take 12 and multiply it times everything, and that includes the 6, I see in the problem. Because what I'm going to see happen is my denominators are all going to cross cancel away, and I'm going to be left with simpler numbers to work with. So instead of finding a common denominator, making all of these fractions have that same denominator, I'm just going to use that common denominator to get rid of all of my fractions. So I'm going to multiply again 12 times this first fraction, so the 3 and the 12 cancel out to leave me with 4 times 100 minus 4x. So hopefully that's clear. And then I've got my equal sign. I'm going to do the same thing. I'm going to do 12 times 5x plus 6 over 4. So this time I'm going to be left with a 3 when I do my cross canceling. So I'm going to have 3 times 5x plus 6. And then I don't want to overlook that I have to take that 12 and multiply by the 6 as well. So I have 12 times 6 with nothing cross canceling away. So as you can see, this is now a pretty ordinary equation. We've got to distribute here, we've got 400 minus 16x. We have a little bit more distributing to do, 15x plus 18. And then we've got 12 times 6 is 72. And so now we just have to gather all of our variables on one side and all of our numbers on the other, and then we're in pretty good shape. So I'm going to add 16x. I'm a fan of having my variables end up positive. So that means I'm going to have to take this 90 here. 72 plus 18 gives us 90. So I'm going to subtract 90 from both sides. So I end up with 31x over here on the right, and that was a 90 there. 400 minus 90 is 310. And so then just divide by 31, and so we get x equals 10. So again, I think a nice technique that we can deploy here on a problem like this, so that we're just working with integer values, is to multiply everything by the common denominator over 1. Where this technique really helps is in an example like the next one, where we have variable expressions in our denominators. And so to find a common denominator and then combine these fractions on one side and the other, it's just not worth it. We might as well just multiply everything by that common denominator over 1, eliminate all of our denominators, and then again be faced with a much simpler problem that we have to solve. So in this case here, I need to factor this denominator. So I got x plus 2 times x minus 2, and then I've got x plus 2 and x minus 2 as my other denominators. So I can see that my common denominator is going to be x plus 2 times x minus 2. And so I'm going to multiply everything by that over 1. So I'm going to use the same approach as I did previously, where this whole expression multiplies each of the 3 fractions. So in this first case, I'm going to cross cancel the x minus 2's, so I'm going to be left with just x plus 2 times 1. It's going to be equal to, now I'm going to do the same thing here. So now the x plus 2's are going to cancel out, but I still have 3 times x minus 2. I do reset every time to the original thing that I'm multiplying by, the x plus 2 times x minus 2. And then finally, x plus 2 times x minus 2 cross cancels with the whole thing here, so we just have minus 6x. So the entire denominator cross cancels with what we're multiplying by, so we just have that minus 6x. So again, I've taken a problem that looked hideous just a moment ago, and I've turned it into something that's quite ordinary. So on the left side, I just have x plus 2. Got a little distributive property here, so I get 3x minus 6, and then still this minus 6x. I'm going to gather my like terms over here on the right hand side, so 3x minus 6x is negative 3x minus 6. Now again, I've got to gather my variables on one side, so this time I'm going to move the x's to the left, so they'll be positive. I'm going to move my integers to the other side, so I've got 4x equals negative 6 minus 2 is negative 8. Divide both sides by 4, and x equals negative 2. Now, unlike the previous question, where there was never an x in the denominator anywhere, if I have an x in the denominator of the original equation, I have to check to see if my solution is what we refer to as extraneous. I need to check to see that it doesn't result in division by 0 in any of my denominators. And so if we take a look at this one, if I plug in negative 2 for x here, I'm okay. Negative 2 minus 2 is negative 4. But if I plug in negative 2 here, negative 2 plus 2 is 0. Or if I plug in negative 2 into the last denominator, negative 2 squared is 4. 4 minus 4 is 0. And if there's one thing that we need to make sure that we know is that you cannot, under any circumstances, divide by 0. A hole opens up in the universe, we all get sucked in and die. And so in this case, if I take that x equals negative 2 that I got through completely valid means, but I plug it in and it does not work in my equation, that tells me that my equation is broken somehow. I have to throw this answer away, and it turns out that this equation has no solution. So sometimes we may have multiple answers, only one of them gets thrown away. Sometimes all of them get thrown away. Sometimes none of them get thrown away. But it's something with these rational equations that we always have to look at. We always have to check to see, do our answers result in division by 0 when we plug them back into the original? If yes, we have to throw that answer out. If no, if it just makes a number like I said here, -4, and that was true in all the other denominators, then we'd be just fine. We'd keep that answer.